a heat pump. And we have covered the reverse Carnot cycle for the heat pump and also for the refrigeration. So as far as the COP is concerned, we are getting the COP of refrigeration by looking at the Q1 divided by the sigma W, where the sigma W in this case is the W net in. If we refer to this diagram, that's what we have learned in thermodynamic. Okay, so this is the reverse Carnot cycle. As I mentioned, we have four main components: the compressor, the condenser, the expansion engine, and also the evaporator. So if the cooling effect Q for one is important for us, then the whole system or the reverse Carnot cycle as is referred as the reversible refrigerator. Or if the heating effect is important to us, then the whole thing, the whole reverse Carnot cycle is known as the reversible heat pump. So one cycle can be functioning as two devices. One is two devices. One is as the refrigeration or refrigerator. Another one is for the heat pump. And as for the TS diagram is concerned, so this is how we look at the TS diagram for a reverse Carnot cycle. 1, 2, compression process, 2, 3, condensation process, 3, 4 is the expansion process, and 4, 1 is the heat addition process. 1, 2, isentropic compression, 3, 4, isentropic expansion, 4, 1, heat supply isothermal as a reversible isothermal heat supply, and the 2, 3 is the isothermal, reversible isothermal heat rejection. And if we look at this formula, then this is what we can get for the COP, ref and COP heat pump. This COP is mainly for the general equation. Okay, both equation of the COP ref and the COP HP can be used for reversible and irreversible type of cycle. But for a reversible one, then we can look at the Q and the Q for rejection, Q for supply, and can be prove that the COP for ref is equal to equation 14.1, T1 divided by T2 minus T1 for refrigeration, and then equation 14.5 is for the heat pump. So please take note, the COP, if you write in a function of temperature, T1 and T2, where the T2 is a high temperature, T1 is low temperature, then this is of course for a reversible cycle only. Okay, in this case, we are looking at the reverse Carnot cycle. So we have looked one tutorial question regarding the Carnot cycle, and this I didn't mention yesterday. Okay, this equation. This equation is basically to look on the relationship between the COPHP and for the COP for refrigerator. So it can be written as COPHP is equal to COPref plus 1. Okay, so maybe I can put something right here just for a reminder, just to prove it. Basically, based on the first law of thermodynamics, okay, basically based on the first law of thermodynamics, we will get a Q for refrigerator, which is the Q41, sorry, Q23 minus Q41 is equal to the W12. And then what we do, we divided everything by the W12, which is W12 is the W net in. This is W12. This is also W12. This will give us the COP heat pump. And this will give us the COP for a refrigerator. And this is equal to 1. Therefore, we can write the COPHP is equal to COPR plus 1. Okay, COPR plus 1. So this is what being stated right here, equation 14.6. Then next what we do is we look into the real, right? The real condition of this TH and also the environment temperature. This I have mentioned yesterday. We can see that this 41 is the temperature of the refrigerant, while the T above, which is called as the, in this case, called as the T river temperature, is above the T set for 4 to 1. Why? Because we need the heat transfer. In order to get heat transfer, then we must have the temperature difference. Same goes for the condenser side. The 2-3 is the T set at the condenser, while the cooling air temperature should be less than the temperature of this saturated refrigerant from 2 to 3. Because why? Because we need the heat transfer. Okay, we need the heat transfer. So in order to get heat transfer, then we need to have temperature difference. Okay, so this is our condenser, this is our evaporator. So in order to transfer the heat from condenser to air, we must have temperature difference. And in this case, the temperature of refrigerant is higher than the temperature of air. While at the evaporator side, we can see that this is the temperature of the river water, this is the temperature of the refrigerant in the evaporator. Then if you want to cool down the temperature of the river water, then we must have the temperature of refrigerant is less than the temperature of this river water. Then only we can absorb the heat from the river water. And then after that, after looking at the reverse Carnot cycle, we look at the vapor compression refrigeration cycle, the VCRC. Why we need the VCRC? Because it's more towards the practical type of the cycle. And then what we do, we substitute the expansion engine as a throttle valve, because the most important thing is to get low pressure. From the pressure of condenser, we are going to throttle it, we're going to expand it to the pressure of the evaporator. So this is what we have. We have the throttle valve right here. The same for the 3 other components. We have the compressor, W net in, the condenser, the heat rejected 2-3, and the evaporator heat supplied or heat absorbed Q41. And in this case, we are going to find that the W net in is equal to the W for the compressor, which is a W12. Okay, and for a throttle valve process, from the SFEE, the steady flow energy equation that we apply for the throttle valve, so what you could have in terms of the SFEE, assuming there's no heat transfer adiabatic, there's no changes in kinetic and potential energy, then we are going to have the H3 is equal to H4. Right? And because of these changes of the throttle valve, we are finding that the Q41 becomes smaller compared with this Carnot cycle. This is the 41 process. And for the VCRC, the 41 is being reduced, becomes smaller. Then what we do, we try to increase back the Q41 by moving the point or state 1 to the saturated vapor. And then after that, we try to move further to the right of state 1 to the superheated vapor. Once the state 1 moves to the saturated vapor, then the point 2 or state 2 will become superheated vapor. And then after that, when we put or we take the state of 1 putting at the superheated vapor, then also we are going to find that the state 2 will become more superheated vapor. So the first one, state 1 as saturated vapor. Method 2 or second one, we are putting the state 1 as superheated vapor. So this is the saturated. We increase the Q41 and at the same time, we also increase the W in, the W12. Okay, and the condenser also, we are going to reject more heat. And then after that, we move the point 3 to the left. Okay, and point 1 also we can move to the right, more superheated. Then we look at point 3 where we use the compressed liquid region, or we have the process of subcool, right? Whereby the state of 3 is being moved to the left into the region of saturated, compressed liquid, or the subcool region. Then we have the undercooling of the condensed vapor. So what happened when state 3 is being moved to the left, so state 4 also automatically will go to the left. So we are going to have more heat absorbed Q41. Okay, so that is what we have looked at previously. This example in this text, I hope you all can have a try, but please check the solution and check all the enthalpies given right here. Okay. So right now, what are we going to do is we are going, okay, just omit this presentation of the table in the text, because we are not going to use this kind of table in the text. We are going to use the table that we are using in the thermodynamic from the Yunus Chenge textbook. Okay, so let us continue with yesterday's question. So before we begin with this, we continue with this question. Do you have any question? Guys, do you have any question?
No, sir.
Okay, thank you. So this is a commercial refrigerator with R134A as the working fluid. It's used to keep the refrigerated space at minus 30 degrees C. So the minus 30 degrees C is the refrigerated space. So maybe what I can do is just to put a chamber right here. This is the chamber. In this chamber, we want to maintain minus 30 degrees C. Right? Then, by rejecting waste heat to a cooling water that enter the condenser at 18 degrees C at rate of 0.25 kilogram per second and leave at 26 degrees C. So this is what being sketched and put all the data in this schematic diagram. The refrigerant enters a condenser at 1.2 megapascal and 65 degrees C, input to the condenser, which is equivalent to the outlet from the compressor. The inlet state of the compressor is 60 kPa and 34 degrees C, and the compressor is estimated to gain a net heat of 450 from the surrounding. So we have a gain of heat by the condenser because the condenser is cool, then some of the heat transfer from the environment or the surrounding will be taken up by the refrigerant in the compressor. Right? So based on this, first question is to get the quality of the refrigerant at the evaporator inlet. So we have looked right here. We have found that the X4 by using the formula as H4 minus HS4 divided by HFG4, and to obtain the value of H4, which is equal to H3, and H3 in this case is undercool or subcool condition. Because why? Because the T3 is less than the T set at the pressure of 1.2 megapascal, which is the pressure of the condenser. And in this case, we are going to get the H3 based on the temperature of the subcool. So this is H3 is equal to HF at 42 degrees C, the outlet condition or the outlet temperature of the refrigerant from the condenser. So when we have H3 which is equal to H4, then putting all the figures, we are going to get the H4 equal to 0.4797. Okay. Then next we are going to look at the part B, the refrigeration load. So if we look here for part B, the refrigeration load is known as the Q dot for 1, which is equal to the M dot of the refrigerant multiplied by H1 minus H4. That is our Q for 1. Okay, our Q for 1. In this case, the M dot is M dot for the refrigerant. Okay, we should get the M dot for the refrigerant. And if we look right here, there is no info on the M dot of the refrigerant. But what we have right here is the M dot for the cooling water. Right? So what we have to do is we have to look at the energy balance of this condenser. So by assuming that this condenser is being insulated, okay, assume that the condenser is insulated. So what happened in this condenser, all the heat rejected by the refrigerant is equal to the heat absorbed by the cooling water. Right? So we could write the equation here. The Q of the cooling water, Q dot cooling water, is equivalent to the Q dot of the refrigerant from point 2 to point 3. Or we can use the energy balance for the heat exchanger. Okay, we can use the energy balance for the heat exchanger. So for the heat exchanger, if we apply the energy balance equation for the heat exchanger, so what we have right here is the energy in is equal to the energy out. So what is our energy in? The energy in is basically the energy input or the energy in by the refrigerant which is the M dot. Okay, let me put right here, this is the refrigerant mass flow rate. This is M R H2 plus the mass flow rate of the water multiplying the enthalpy inlet, which is equal to the M dot R H3 plus the M dot W H naught. Okay, so this is what we can write. Basically, look at the energy balance of this condenser. So what is coming in to the condenser as far as the refrigerant is concerned, this is M dot R. Outlet right here is M dot R. So inlet M dot R H2 plus M dot W H I equal to outlet M dot R H3 plus M dot W H naught of the cooling water. Okay, and when we rearrange this equation by putting the M dot Q dot CW to the left, what we have right here is the M dot cooling water H I minus H naught, M dot cooling water H I minus H naught, okay, which is equal to the M dot R H3, this is H3 minus H2. Okay, so basically what is this? This is the Q dot cooling water. And what is this? This is basically the Q dot of 2,3. Okay, so in this case we are going to get the negative sign, okay, because HI H naught, the HI is less than the H naught because this is at low temperature, this is higher temperature. So same goes for this. So we are going to have minus minus. So the minus sign we cancel off. And finally, we'll get QCW equal to Q dot 23. Okay. So in order to get the M dot R, so this is our M dot R that we want to obtain in order to solve for the part B. Okay, part B is to get the Q41, then the M dot R is equal to M dot W HI minus H naught divided by H3 minus H2. Alright? So we already have the H3. Now we have to get what is H2. Okay, we have to get what is H2. So in order to get the H2, we need to look at this compressor side. Okay, compressor side. So remember, we have the heat gain right here. So if I can sketch back the compressor, to sketch the compressor. So this is our compressor. Okay, this is state 1. This is state 2. This is the work input to the compressor, W12. And remember, we have the heat gain, Q dot gain. Oh, meaning that we need to get two equations, because in this case, the H3, okay, no problem. The H2, if you look right here, the H2, we also need the M dot. Let us look the energy balance first for the H2. The energy balance for the H2, we look at the compressor. And this is M dot R, okay? M dot R H1 plus W dot 12 plus Q dot G equal to M dot R H2. So again, we have our M dot R. So we need to solve for the M dot R. Here also we need to solve for the M dot R. Wow. Guys, we have two unknown. We have two equation, two unknown. Two equation, two unknown. Let's put this so this is M dot R H1 minus H2, which is equivalent to, this case is this is our M dot. M dot R H1 minus H2 equal to minus W dot 12 minus Q dot G. And in this case, we are also having problem of M dot R. In this case, we cannot solve the M dot R right here. Aha. Anybody have any idea how to get the H2 and also the M dot R? Let me see. This one is soft. This is soft. This is soft. So we need H2. In this case, this is equal to H1 minus H2 is equal to minus W dot 12 divided by M dot R minus, this is Q dot divided by Q dot G divided by M dot R. Don't know what is MR. And we do we have the W12? W dot 12? No also. Hang. Oh, sorry guys, the H2 is given. Alamak. Why do you say it to me? We could get H2, H2 in this case. So we know we don't need this extra equation for this one. Okay, sorry guys. We could solve for the H2 because the H2 condition is given. Sorry, my bad. Because I don't look at the detail of the state 2. Okay, so let us get the what is H2. The H2 is basically look at the condition of the H2 we have given right here. The H2 is 1.265. 1.2 megapascal, 65 degrees C. Okay, so if we look at a 1.2 megapascal, 65, for sure we are going to have superheated vapor. Why? Because we are going to get the T2 is greater than the T set. Therefore, it's superheated vapor. So let us look at the table of refrigerant. This guy get for me what is a H2? 65, 1.2. 65, 1.2. 1.2, this is 1.2. 1.2 is right here. 1.2. Okay, 65 is not been tabulated. Okay, 65 is not been tabulated. So what we have to do, we have to make interpolation. So 65, we want the enthalpy. This is 65. Point. Copy. B. So please get what is the enthalpy? Log right here. So where is our 65? This is our 65. Then we need the value of enthalpy. This is our enthalpy. This is H2. So please get the H2 for me. Okay, berapa? Anybody? 5 divided by 10. Ya, berapa? Yes, anyone?
295.13.
295.13. Okay, thank you. Okay, now get your envelope out. Before that, we need to find what is HI and H naught. What is HI and H naught? So we can find that the the temperature, right? The temperature for the cooling water, one is at the cooling water, the temperature is 18 degrees C and the temperature is 26. So this is just a cooling water, assuming that the temperature, the pressure is ambient pressure, and we can find that the state of I and naught for the cooling water is compressed liquid. Okay, is compressed liquid. So in this case, we are going to have the HI. HI is equal to HF at, how much is it now? Forgot it. The temperature is 18 and 26. 18 and 26. 18 and 26. Both is in compressed liquid region. So we need to get from water, for the water. So we need to get the temperature, the table for water. So this is 18. Oh, again, we have to interpolate. So we need the HF. So at 18 and 18, here is 18. So we need the HF. So this is our HF. Copy 1520. This is not the one. Water. Water 2015. So get what is the temperature? This is at 15 degrees C. This is 20 degrees C. So we want the at 18 degrees C. So please interpolate to get what is the value of HI. And as for the H naught, for water is at 26 degrees C. Oh, semua tak ada ni. Apa cerita ni? Alamak. Semua kena interpolate. 26 degrees C. 26 degrees C. Yeah, this is the one. HF. This one. The 26 degrees C. This. Okay. This is at, here is our 26 degrees C. So please interpolate, get for me. So this 26 is in between, 26 is in between 25 and 30. This is in between 25 and 30. 25 and 30. This is 25, this is 30. You want to get at 26 degrees C. Okay guys, so what is HI? HI, this is H naught. Okay, please calculate for me. Anyone? HI?
75.54.
75.54.
54.
H naught?
109.012.
109.01.
012. Yeah.
Okay, thank you. So now we have all the values, then put inside this equation, then try to get what is m dot r. The m dot w is 0.25. M dot r is equal to 0.25 multiplied by this h I minus h naught, right? H I minus h naught. H I, yeah. H I minus h naught. 75.54 minus 109.01 divided by the H3 minus H2. H3, do we have the H3? Yeah. H3 is 111.26. 111.26. 111.26. 111.26 minus H2 295.13. What is our M dot R?
0.04551
kilogram over second. Now only we are going to look for the H2. Remember, the question is asking for Q41, eh? This one. So we already have the Q41. Sorry, the M dot R, then H1 minus H4. Do we have the H1? Yeah, this is our H1. Do you have the H1? Tengok, guys. H1 tak lagi, eh? H1 tak lagi. Okay. So we need to get the H1. So what is H1? H1 is basically based on the pressure of our condenser. Pressure of condenser is 60 and minus 34. 60 minus 34. This is 60 minus 34. kPa. What is H1? 60 minus, is superheated vapor, right? So before that, we need to look at the T set at 60 kPa. T set at 60 kPa. T set at 60 kPa. This is 60 kPa. T set is minus 36.95. 36.95. 36 minus 36.95 degrees C. So we could get here is the T1 is greater than the T set. Therefore, superheated vapor. So when we got superheated vapor, then we are going to look for the superheated at 60, which is 0.6. 0.6 at 34. 0.6 at 34. 0.6. Again tak ada juga. Banyaknya kena buat interpolation. Sorry lah guys. Very good question we try to avoid a lot of interpolation but in this case sorry lah. Maybe I got the wrong question. I give you the wrong example. Okay, 0.6, 34. So we need this one. The enthalpy. Which one? Check again. For refrigerant, 0.6, yeah, 270, 30, 40. 30, 40. This is at 30, is at 40. We want to get at 34 degrees C. This is our H1. You guys, please interpolate. Get the H1. Oh. Salah
Bukan negatif.
negatif lah.
34.
Negatif. Negatif. 60 kPa 0.06 Alamak. 0.06 kan? Guys? Guys?
Yes, sir.
Alamak. Tak ada data lah. This is okay. We use this one. Sorry. Sekejap This whole thing is wrong. We should refer 0.06. This one 0.006. So kita ada 34. Ni 36. Okay. Print screen. Paste. Okay, kita punya, this is at saturated So let me copy everything supaya nampak jelas. Okay. So this is the whole thing. Kita nakkan dia punya enthalpy. Okay, copy. Yes. So guys, right now, where do we need to interpolate? Where is minus 36? This is, this is the T set, right? Minus 36. So now the set value, the T set is this value. Okay? That is the value. So where is our 34? Minus 34 is at this slot. Minus 34. Minus 34 is in between minus 36.95 and minus 30. Okay? So the value of enthalpy that we want is this. This is the enthalpy. This is U, this is V, U. That's one. Okay? So if I could write it clearly, let me write. So this is our H1. So H1 minus 227.79 divided by 240.76 minus 227.79, and this is equal to minus 34 minus 36.95 divided by minus 10, no, sorry, minus 20, minus 20, minus 36.95. Check again. This is H1 minus this, okay. This minus this, divide this minus this, okay. Equal to this minus this, divided by this minus this, okay. That's correct. So please get the H1. Okay, anyone? What is H1? Okay, saya boleh dapat H1?
230.05.
230.05. Betul tak? Dia must be in between. Okay, that's right. So now get our Q dot for one. M dot R. Let's show M dot R. 0.044511. 0.044511. 5.1 minus minus H1 minus H4. Okay, H1 minus H4. H1 230.05. H4 is equal to H3. Okay, H4 is equal to H3. Where is our H3? 111.26. 111.26. So calculate what is the Q41? Betul tak guys? Yang apa ni? H3 is 111.26 kan?
Betul.
Okay. So how much is the Q.41? Okay, anyone?
Five point 406.
1.5
5.406.
eh?
Yes.
5.4.
406.
4 eh? 4
Yes, yes, bro.
06.
Yes.
Okay, thank you. Kilowatt. Okay. That is for the refrigerated ataupun yang dikatakan sebagai apa? Dikatakan sebagai in this case refrigeration load. Okay, now we want to get what is the COP. Right, so I need this diagram. So I will solve it by this side. Okay. So part C is to get the COP for refrigeration. This is equal to Q dot 41 divided by the W dot 12. So we are getting the Q dot G right here. So we need to put the Q dot G in our energy balance. So if we look at the compressor, SFEE, then what we could have right here is the M dot R H1 plus W dot 12 plus Q dot G equal to M dot R H2. So we want to solve for what? We want to solve for W12. Then the W12 is equivalent to M dot R H2 minus H1. Okay. Minus Q dot G. Okay, so this is W12 this is in, the energy transfer in, this is initial energy, this is final energy. So M dot R, W12 equal to M dot R H2 minus H1 minus Q dot G. So we have all the figures. What is the m dot r? The m dot r just now we got how much? M dot r. We got the m dot r as 0.0551. 0.04551. 0.04551. H2, we have the H2. The H2 is 295.13. 295.13. 295.13 minus H1. The H1 23005. 230.05. So what is our W.12? Okay, how much? Oh, sorry. I left one thing, this one. This is 450 divided by 1000. Forgot to put the Q dot G. The Q dot G is the heat gain is 450, right? Okay, how much is that?
Uh, 2.5,
2.5, 118.
8, 2.5.8.
2.5.8.
Yeah.
Satu lagi?
No, sir. 2.5118
Oh,
kilowatt.
2.5118. 2.5118. Tu lah. Betul? Betul ke?
Yes.
Okay. So now we get the COP. What is COP? COP R is equal to, what is our Q for 1 just now? Q for 1 is Q for 1. Q for 1, 5406. 5406. Sorry. 5.406. Q for 1, 5.406 divided by 2.512. What is COP?
$2.152, sir.
Sorry, again? Amirul?
2.152.
2.152. What is the unit of COP? What is the unit for COP? there is no unit. Okay, there is no unit. Okay, let me add up a question. This part D. I want to know what is the COP R maximum. So the COP R maximum should be the COP R for a reversible cycle which follow the reverse Carnot cycle. So this is equal to T1 divided by T2 minus T1, where the T1 is equal to the T set at what is our pressure of condenser? The pressure of condenser is 60 kPa. What is T2? T2 is equivalent to the T set at our high pressure is at 1.2 megapascal. So what is that? 60. Just now we have got it. So at 60, we got 30 degrees C. Oh, this is we are using the value of the environment, minus 30. So this is at the space. The space, the cooling space temperature. And our T2 is basically based on the temperature input to our water. Minus the T1 again is minus 30. So please get what is our, not this one, not this one. Sorry guys, this is for the refrigerant. Okay, this is for the refrigerant, but in our case, we need to get what is the environment and the space. Okay, the space temperature or the cooling space temperature. So what is our COP? Next.
Five 5.063.
Okay. And this is the temperature of the water, cooling water. Right? And then I add up one more question. What is the COPHP? The COPHP is equal to the COPR plus 1. So COPR is 2 something, then plus 1. This is a 2.152 plus 1 is equal to 3.152. Okay. So now let us sketch process. On TS diagram. TS. Our condenser pressure. Sorry, the evaporator pressure. The condenser pressure. Okay. State 1, superheated. what I'm going to do right now. I need to lower down the pressure. Right? Okay. Let us look at the process of at the compressor. Is the compressor is adiabatic? Is our compressor adiabatic? Guys, is our compressor adiabatic? Adakah kita punya compressor tu adiabatic? Tak ada kan? Because we got the Q dot gain. Okay? Jadi maknanya our process is a non-reversible. Right? It's non-adiabatic. Maybe it's reversible but non-adiabatic. Because of non-adiabatic, kita akan dapati ada irreversibilities. So the actual process for the compressor, we have isentropic efficiency right here. 1, 2. And this is our 2S. Okay. Kalau kita lihat our process or compression process is non-adiabatic. Maknanya ada heat gain Jadi maknanya sekarang ni dia bukan isentropic process. Right? So 1, 2 is the dotted line, that the actual process for the compressor. And then 1, 2S ni adalah the isentropic. And then kita dapati bahawa kita subcool. Okay. We have a subcooling at our condenser outlet. Okay, this is the subcool. Then kalau ada subcool, this is our beginning of 0.3 to 0.4. This is 0.4. This is 0.3. So this is our degree of subcool. Yeah. This is our degree of superheat. Okay, this is degree of subcool. This is degree of superheat. Jadi this is our process. This is at the condenser. Okay. So you need to label all the temperature involved and the pressure involved. So this is our P1. This is our P2. So this is our T set. This is T set. This is our T3. This is our T set. This is our T1. Okay. So this is the TS diagram. Now, in thermodynamic, for refrigeration, we are going to learn another property diagram. Okay, we are going to learn another property diagram. And the property diagram is called as the pressure against enthalpy. Yeah, it's a pressure against enthalpy. So let me continue to the bottom part. Okay. Pressure against pressure enthalpy. So let me sketch. We try to look at the profile first. This is called the pressure enthalpy. Why we need to get the pressure against enthalpy? Because we know that every Q and W is involving the enthalpy. So when we draw our saturation line, this is how we draw our saturation line. Okay, there is the saturation line. when we sketch our pressure, of course, the pressure will look horizontally. So this is the pressure constant. Of course, vertically is our enthalpy constant. And the third property that we are interested to sketch on a pH diagram is our temperature line. So the temperature line will look like this. It's a vertical. The temperature line is vertical at the compressed liquid. Then we have the phase change line, which is horizontal. Phase change, we know that the phase change will occur during T constant. And at the superheated vapor region, this is a curved type of profile. So this is our T. So this is the profile. pH diagram, pressure horizontal, enthalpy vertical, and the temperature line vertically at compressed liquid, horizontally at the mixture, and is a curve going downward at the superheated vapor region. Okay? So we try to sketch this process, this particular question on a pH diagram. Now we are going to convert the TS diagram to the pH diagram. So this P and this is our H. This is our saturation line. Our pressure (1,200 kPa). This is in kilojoule over kilogram. And then we have another line. This is at 60 kPa. Okay. And then we try to sketch this is the T set line. Okay. And this is the actual temperature of 1 minus 34 degrees C. Okay. And when we look at the condenser outlet, this is our T set. Okay. And then we have our actual temperature going into the throttle valve or outlet of the condenser. This is at 40 degrees C. Correct, eh? 40 kan? Sorry, it's not 40, it's 42 eh? Guys, 40 or 42? Guys?
42, Doctor.
42 eh? This is a 42 degree C. So our concern is, this is state 1. This is state 3. And when we sketch the isentropic compression, it will look like this. This is our 2S. Let me put it there. So this is 2S. And this should be our actual. Okay, so this is isentropic compression. This is the actual compression. And then we have the condensation process at the condenser. Begin at point 2. This is our condensation process. Up to point 3. After that, we have our throttling process. 4. And then we have our evaporation process at the evaporator. So that is how our pH diagram look like for this question. Okay, for this question. Hey guys, any question? So if we have this type of diagram, then if to me, I will add up one more question. The F part. Get the isentropic efficiency of the compressor, which is equal to the isentropic compression 1 to S divided by the actual compression. So this is H1 minus H2S, sorry, H2S minus H1 divided by H2 minus H1. So remember, we have solved for the H1 and also the H2. So now you have to get H2S. I'm not going to solve it, but I'm going to show you how to get the H2S. Basically, the H2S, we are going to use based on the 1.2 megapascal and also the S2S, which is equal to S1. So the H2S you are going to get based on this 1.2 megapascal, and the S2S is equivalent to S1, and the S1 is at superheated region at 60 kPa minus 34 degrees C. So from here, you will solve the H2. Then after that, you will solve for the isentropic efficiency of the compressor. Okay? Any question? Any question, guys? No question.
No, doctor.
Okay. You. Okay. So that is the example question. This question, I will treat it as a level of exam question, and the difficulties is moderate. Okay, the difficulties is moderate. Okay. Now, let us look at the state 4. If you look at the TS diagram, TS, okay, this particular cycle, let's say this is our cycle. This is 1, this is 2, this is 3, this is 4. If I sketch on a pH diagram, this is P, this is H, this is our saturation line. Okay, this is our pressure level. So I will have this type of cycle. So this is a pH diagram for saturated. The condition of this 0.1 is saturated vapor and 0.3 is saturated liquid. Let us look at state 4. If I take a container or a chamber and I put this state 4 inside the container or inside the chamber, what could I have? I can see that at this state 4, I'm having a two-phase type of liquid plus vapor. Okay, liquid plus vapor. This is our saturated vapor. Actually, we refer this as mg, and this saturated liquid we refer as mf. Okay, and f. So when I heat it up, okay, when I heat it up, can you describe what is actually happening at the R134A? Anyone can explain to me what happened? Anyone can explain what happened when I have this heating process of this state 4? Can someone explain to me what happened? You guys? Guys? Can anyone explain what actually happened when I have state 4 and I heat it up? What happened? Guys? Hello guys? Calling. Anyone?
More gas?
Pardon?
More gas?
I couldn't hear you clearly, Naveen.
More gas?
More gas. How come we have more gas? How come we have more gas? Because the liquid part is going to be converted to saturated vapor, correct?
Yeah.
Yes. Meaning that when I heat it up, what happened to this mg? This mg. What happened to this mg?
Fade.
The mg, the first portion of the mg, it will remain the same, correct? Let's say this is the part of the mg, the initial mg. Okay, let me put, I put a partition right here. This is the original mg, which exists in state 4. Okay, which exists in state 4. This is the one. And then what happened? The part for the mf will be reduced. So this is the part where we reduce the mf. So this is state 4. Heating it up. Now this is state 1. Okay, this is state 1. Right. So when the mf is reduced in state 1, meaning that we have more let me put different color. Okay. Do I have okay, different color. So what actually happened? Initially, we have state 4. This is what we can see because 4 is a mixture. We have m dot f at point 4, state 4. We have m dot g. We have mg at state 4. Now, if we look right here, what actually happened from point 4 to point 1 actually is a heating process. Okay, actually is a heating process. So this is our heating process, Q41. We are going to absorb heat right here during the process, which is Q41. So the only portion, the only parts that play an important role of absorbing this Q4 is actually the liquid phase, where it will be converted to this vapor phase. Okay, so from this process 4 to 1, again I repeat, this process of 4 to 1 is actually only affected the portion of MF. The MF now is being reduced, and the reduction in MF at state 4 will become the saturated vapor, which I represent as in green color right here. Okay. What is actually happening of the Mg? Does this Mg at state 4 play a role in absorbing the Q41? Guys, does this Mg portion play a role in absorbing the Q41?
No.
No. Okay? No, it doesn't play any role in the process of absorbing the Q41. The Mg at state 4 just follow without playing any role, just follow. Okay, so it is a very wasteful type of process because it does not play any role. Okay, any role. So what happened? What we do right now, we are going to separate this Mg and this Mf. Okay, we are going to separate this Mg and this Mf. We want to separate so that we have more efficient the process of absorbing heat from the process from the state 4 to state 1. Right? So this is done, the separation process is done in a component called flash chamber. Yeah? A component called flash chamber. Why this called flash chamber? Because in the throttle valve, this flashing of vapor is happening from state 3 to state 4. Okay, the flashing of vapor. Actually, 3 to 4, we don't put any energy in. But because of the sudden change in pressure, we are going to have this vapor. I don't know, you guys, do you have the experience of opening a can of carbonated soft drink or a can of soda? If I ask you, do you have the experience of opening a glass bottle? I don't think you all have the experience. Remember, guys, I don't know, during my teenagers, during my childhood, we do have glass bottle of soft drink, whereby we have a cap right here. Okay, we have a cap, and this bottle is reusable. Reusable. This cap. This is a glass bottle. But right now, I don't think that we don't have this kind of glass bottle anymore. Everything is being converted to plastic. I don't know whether the plastic can produce what I'm going to explain here. I don't know. But what happened is actually, when we take off this cap, the cover of this bottle, sometimes what we can see, a saturated condition of this bottle, of this drink in this bottle. Maybe right now also you can see when you have a can. Okay, you have a drink in a can, and you have your pin right here. When you take it off, the pin or the ring, you can still see some vapor coming out from this. Okay, why? Because initially the pressure inside the can or in the bottle is higher than the atmospheric pressure. Okay, higher than the atmospheric pressure. So when we have a sudden change from high pressure to low pressure, there are some flashing of this vapor. Okay, there are the flashing of this vapor. So what happened? In our case, the same thing. High pressure to low pressure, we have the flashing of saturated vapor. But we want to heat up, or we want this state 4 to absorb the heat. This Mg does not play any role in absorbing the Q41. So right now, what we are going to do, we are going to separate these two parts. Okay, we are going to separate these two parts, the saturated vapor and the saturated liquid. The saturated vapor, we are going to a second stage compressor, while this M.F, we are going to flow to another one throttle valve. Then only we are going to flow in the condenser. Okay, So this is called as a two-stage compression cycle, which incorporate what is being called as the flash chamber. So this can be seen from these notes from our textbook. This I have explained before. This is our pH diagram. This is the pH chart. Okay, this is the pH diagram. This is the pH chart. Okay, this is the pH chart. We're going to omit on the compressor type, but what I'm going to do right now to look at the flash chamber. Okay, this is the use of flash chamber. This part is what I explained just now about the state 4. Okay, I explained just now about the state 4. So what we are going to do, we are going to use a flash chamber. And this flash chamber is to separate the vapor phase and the liquid phase. The vapor phase, we are going to flow the vapor phase to a second compressor. But before entering the second compressor, it will be mixed with the refrigerant which being compressed by the first compressor. Okay? And the liquid, the MF, being throttled in the second throttle valve, then we are going to have the evaporation process. So what happened? We are going to have the same compression process, which is 1 to 2, 5 to 6. Okay? As far as the compression process is concerned, the work involved is still to compress from the evaporator pressure to the condenser pressure. That is the limit of our compression process. It's all depend the minimum pressure, which is the evaporator pressure, and the maximum pressure, which is the condenser pressure. Okay? The most important thing, what you want to look right here, is to increase the cooling effect. If we don't separate, okay, if we don't separate these two phases after the expansion process at the throttle valve, this is what we're going to have. This is the point 4. But when we use this flash chamber, what happened? The MF will be flow to the left, which is the condition is saturated liquid. Then we are going to expand in the throttle valve, and we have the point 4 is bring to the left. So compare this enthalpy and this enthalpy, we are going to have the increment of Q41, right? So the Q41 is being increased, or Q41 is increases with the same amount of work input to the system. Therefore, this particular plant or this particular refrigeration plant is to increase the COP. Okay, so this particular plant or this particular new cycle with new schematic is purposely to increase the COP, right? by increasing the Q41, the refrigerating effect, while maintaining the same power input to the compressor. Right? Whereby in previous lecture, what we do, we try to modify the whole cycle by looking at state 1, bringing it to the right, or increasing Q41. But that case, when we increase the Q41, we also increase the work input to the compressor. Same goes for the state 3. When we move the state 3 to the left, right, meaning that we also, with the same amount of work, we are also increasing the COP. But when we move the point 1 to the right, we only increasing the Q41. There's no effect on the COP. Because we the same time we do increase the work input. But if we bring the point 3 to the left, the work input maintain the same, but we increase the Q41. So you need to understand which alteration or which modification will increase the COP and also for the increase of Q41. So you need to differentiate instead of that. Look which one, Q41 increase or COP increase. Of course, if we want to increase COP, we need to increase the Q41 or reduce the W input. But in this case, we are not going to touch anything on the decrease of the power input. So this is our schematic diagram for the new cycle, which is called as the two-stage compression process with flash chamber. Okay, with flash chamber. So I think we stop right here and we will continue on Wednesday. Any question, guys? Attendance Monday.